Hey students, in this video we're going to talk about partial derivatives. So a partial derivative for a multivariable function is the derivative with respect to a particular variable. Generally, we're going to be using x and y. So when we see the notation fx of xy, for instance, this is going to mean the first order partial derivative with respect to x, meaning we only differentiate terms that contain an x, and terms that do not contain an x, their derivative is zero because the other terms are considered constants. The derivatives of those terms are considered zero. So for our first example, we have to determine the first order partial derivatives for the function. So So for f(x) of xy, the only term that contains an x is the 3x squared, so its derivative is just 6x. Now, if we're looking for the partial derivative fy, all right, so this should be a subscript too, just so there's no confusion. This is a subscript of y, so fy of xy is now the only term that has a y is the 4y cubed, so its derivative is 12y squared. And that's how we do a partial derivative. So we're using the same rules that we have for the derivative of a single variable for a multivariable function. So for example 2, we have to find the first order partial derivatives, and we'll go back and forth with colors so we can make sense of it. So when we're finding fx of xy, the 3x squared y and the 2x both contain an x, so those are the terms we use for our derivative. So the derivative of 3x squared is 6x. The y, which is a constant, just comes along with it, and then we add the derivative of 2x, which is 2. For our fy, we can erase the terms we underline for fx. For fy, we have a 3x squared y term and a y term. So now our partial derivative with respect to y is going to be, the derivative of y is 1, so we're going to have 1 and we multiply it by 3x squared, plus the derivative of y is also 1. So that just gives us 3x squared plus 1. So we can see that doing the partial derivatives is just like doing the derivative for a single variable, except we just basically ignore the other variable if it's not in a product with the variable that we are differentiating. So because we have two partial derivatives, when we get to second order partial derivatives, there are two possibilities. So like we'll say for this the red function, we could do a second derivative with respect to x, or we could do a second derivative with respect to y. And then for our green function, we could do a second derivative with respect to x again, or we could do a second derivative with respect to y. So that's always going to mean that we get 4 second order partial derivatives. The order of the variables tells you which way, the order to find the derivatives from left to right. So if we saw something like f of x, y, x, x, for instance, that's going to mean the first derivative is for x, the second derivative is with respect to y, the third derivative is with respect to x, and the fourth derivative is also with respect to x. But generally, we won't go that far. So for our third example, we want to find all 4 second order partial derivatives. So first, let's find fx. So fx of xy is, so that term and that term both contain an x. So that's going to give us 10x to the fourth y cubed plus 6xy. And we'll write the partial derivative for y beside this. So then for fy of xy, we're going to get 6x to the fifth y squared plus 3x squared. So now when we're finding our first, we're finding the second derivative with respect to x, we're going to get fxx of xy is, so we would get 40x cubed y cubed plus 6y. And then for fy of xy, we're going to get 12x to the fifth y. And the derivative of this term is going to be 0 because it doesn't contain an x. I'm sorry, it doesn't contain a y. And so our second derivative of the derivative of the first order partial derivative with respect to x, our f of xy, is going to be, so now we're taking the derivative of this equation with respect to y. So 3 times 10 is going to be, we're going to get 30x to the fourth y squared plus the derivative of 6xy is 6x. Over here, when we find the derivative with respect to x of fy, so fxy is going to equal 5 times 6 is 30, so we're going to get 30x to the fourth y squared, and then the derivative of 3x squared with respect to x is 6x. Notice for our second order derivative, the mixed derivative, we got the same thing. And this is called our mixed second order derivative. Notice that they are the same thing. And generally, that's going to be true. So look out for that. If you get two different things for that mixed derivative, it's a good indicator that you've done something wrong in one of the derivatives. For our fourth example, we want to find all second order partial derivatives. So for fx of xy, we're going to get, so the derivative of sine is cosine, and so we have cosine xy, but remember, chain rule, you have to multiply by the derivative of the angle, which is xy. And the derivative of xy with respect to x is just going to be x times 1 times y, which is going to give us y. And so now when we find our second derivative with respect to x, we're going to get, so the derivative of cosine is negative sine, so we're going to get negative sine xy time. We already have this y at the back. You know what? Let's actually do a rewrite for a moment. So we're going to rewrite this so that it's y cosine x is y cosine xy. And so the derivative is still going to be y. So the y is going to come along as a constant. But then we multiply by the derivative of cosine xy, which is negative sine xy. And again, we multiply by the derivative of the angle. So we multiply by y again. And we're going to get negative y squared sine xy. So if we find our mixed derivative, f of fxy of xy, now we have to do the product rule because we have y times another function that contains a y. So the derivative of y is 1. We multiply that by cosine xy plus y times the derivative of cosine xy, which is negative sine xy times the derivative of xy with respect to y, which means that we multiply by x. So our mixed derivative is cosine xy minus xy sine xy. So those are all our derivatives if we led with x. So our partial derivatives for y, fy of xy, we're still going to get for the first one cosine xy. But now the derivative of xy with respect to y is going to mean we multiply by x. Our second derivative with respect to y is going to be, so we keep the x, multiply by the derivative of cosine, which is negative sine xy, but then we multiply by the derivative of xy with respect to y, which is going to be multiplying by x again. So we get negative x squared sine xy. So now for our mixed derivative, we should get this, but we're going to do one more to verify that that's actually true. So if we start here for our second derivative, fyx, the mixed derivative, is going to equal, so now we're taking the derivative of the y derivative with respect to x. We're going to get, so the derivative of x is 1, we multiply by cosine xy plus x times the derivative of cosine xy, which is negative sine xy times the derivative of xy with respect to x, which is going to mean times y. So we end up with cosine xy negative xy, so minus xy sine xy. So notice again, we got the same derivative for our mixed derivative. Cool. For our next example, it's just a review of some of the basic rules for other functions like e, and later on we'll see a logarithm. So the process of partial derivatives works for however many variables you have. When you're finding that partial derivative, you treat all other variables as constants. So we want to find the 4 first partial derivatives for this function. So one thing I would say is let's rewrite this so that it is wx times e to the z plus e to the y squared to the negative 1 power. I can write that better though. That looks bad. So we'll say that is wx times e to the z power plus e to the y squared power to the negative 1. It's going to help out for like chain rule stuff. All right, so the partial derivative w, x, y, z with respect to w is going to be, all right, so all of this is a constant then for the w. So it's just going to be x times e to the z plus e to the y squared to the negative 1 power. And then our fx of w, x, y, z is going to be basically be the same thing, but this time the w e to the z plus e to the y squared to the negative 1 is the constant. So the derivative of x is 1. We multiply by the constant, so that's going to give us w e to the z plus e to the y squared to the negative 1 power. Now for our, too big. Now for our partial derivative with respect to z and y, we wanted to have to do the chain rule because our problem gets a little more involved. So that was Wx. All right. So let's say we do the partial derivative with respect to y in red. So Wx, y, and z. So now we have this outside power to worry about. So what the chain rule is going to tell us is that we have -1 times Wx. So -1 times Wx. And remember, you never, for the chain rule, you never change what is raised to the power. We subtract one from the power, and that's going to give us -2. And the chain rule says that we need to multiply by the derivative of the inside. So the derivative of e to the z is e to the z, and the e to the y squared doesn't contain a z, so its derivative is 0. So that's going to be -Wx e to the z. And if we rewrote this so that it looked nice, it would be e to the z plus e to the y squared to the positive 2 power. For these other functions, we could rewrite it so that it's w divided by, for instance, e to the z plus e to the y squared to the first power. And this would be x divided by e to the z plus e to the y squared to the first power. And so our last partial derivative we'll do with respect to z. Let's get that out of the way. So fz of w, x, y, z is equal to, again, basically the same thing. So we're going to have -1 times wx times e to the z plus e to the y squared to the -2 power. But now we're multiplying by the derivative of that term, which is going to be, so for an exponential function, remember, it's the derivative of the exponent times the exponent. The derivative of the exponent times the exponential function. So that's going to give us 2y e to the y squared. And if we simplify that, we're going to get -wx y, we'll slide that 2 in the front, so -2wxy e to the y squared divided by e to the z plus e to the y squared squared. And those are our 4 partial derivatives. So now if we were finding second order partial derivatives, there would be 16 of them. There would be 4 for would it be, you would have FWW, FWX, FWY, FWZ. Yeah, so there would be 16 total partial derivatives, second order. So that's a nightmare. Obviously, we're not going to do that. All right, so for our last example, we want to find that's going to be a lot. So let's find the first order partial derivative. Maybe we'll do a second order for one. So first, let's find fx. So fx of x, y. So now notice we have 2 functions of x multiplied. So this is going to mean product rule. So fx of xy is going to be the derivative of x squared, which is 2x, multiplied by the logarithm of x squared plus y squared, plus x squared times the derivative of the natural logarithm of x squared plus y squared. So remember, for a logarithm, it is the derivative of the input, which for x is going to just be x squared, divided by the input, which is x squared plus y squared. So when we simplify that, we get 2x ln x squared plus y squared plus 2x times x squared is 2x cubed divided by x squared plus y squared. Yeah, so we're not going to do a second order derivative. It'll be too much work. And so then our partial derivative with respect to y So now notice for the y term, only the logarithm contains a y. So the x squared is a constant. So it's going to be x squared times the derivative of ln x squared y squared with respect to y. So the derivative of y squared is going to be 2y, and we divide by x squared plus y squared, which if we simplify, we get 2x squared y divided by x squared plus y squared. So you know what, actually, let's say we did the second partial derivatives for y. So say we found the second order derivative for y. This will give us a chance to review the quotient rule. So the second order derivative for y with respect to y is going to be x squared plus y squared times the derivative of the top with respect to y. So that's going to be 2x squared minus the top, which is 2x squared y, times the derivative of the bottom, which is 2y, all divided by the denominator squared. So if we simplify this, that's going to give us 2x to the fourth plus 2x squared y squared minus 4x squared y squared, all divided by x squared plus y squared squared. And that simplifies to be 2 times x to the fourth minus, so 2x squared y squared minus 4x squared y squared is negative 2x squared y squared. So we're just going to have minus x squared y squared. You know, honestly, we could factor out a 2x squared. So that would give us 2x squared times x squared minus, so again, these together make a negative 2x squared y squared. So this is just going to be minus y squared. Which if you wanted to further factor is x plus y times x minus y, but we'll stop here. And that's over x squared plus y squared squared. So that's the second partial derivative with respect to y. Let's stop here. We could do the same thing for f, y, x, but we won't. All right, so that concludes our video for partial derivatives. It's just like doing derivatives for a single variable, except now the variable has a buddy. All right.